Hello and welcome to another session in physics. In this session, we'll be looking at the topic radioactivity, part 2. But before that, let's review the previous lesson. Welcome back. At this point, let's talk about the artificial transformation and the effects of nuclear energy and what nuclear energy is all about. Artificial transformation and nuclear energy. Remember, in our previous lesson we were trying to talk about what radioactivity was all about and how it refers to the disintegration of atoms and elements with the release of energy. Remember, we said the process of radioactivity is entirely a spontaneous process. And when we say it is a spontaneous process, we mean it is entirely out of the control of physical agencies such as temperature and other things like pressure. So it's entirely an independent phenomenon. It is random. Nobody can tell exactly when the next atom is going to decay or when it will not decay. Now, when we talk about artificial transformation, we are talking about how it is induced in an element by what we call a radiation. A radiation means exposure to radiation, either by accident or by intent. Remember, we said we have two basic types of radiation. We have natural and we have artificial processes of radioactivity, natural and artificial. Now, artificial transformation is induced in an element through exposure to radiation, either by accident or by intent. The first person to achieve this was Rutherford. Now, from his experiment, we came to understand that an ordinary material that is not normally radioactive is made radioactive when we bombard it with radioactive particles. So when an ordinary material that ordinarily is not radioactive is brought into contact or is introduced to radioactivity, either intentionally or by accident, then that particle can be made to become radioactive. Let's talk about nuclear energy. When you hear nuclear energy, what comes to your mind? Well, do you think about atomic weapons? Do you think about weapons of mass destruction? Do you think about nuclear bombs or hydrogen bombs? Back in 1945, during World War II, two Japanese cities, Hiroshima and Nagasaki, were destroyed. In fact, today there is nowhere in Japan called Hiroshima and Nagasaki. These two cities were destroyed when two bombs, nuclear bombs, were released in both cities, and it wiped everyone living in the city, wiped up all infrastructure and rendered the city incognito. That is exactly what can happen when the power of nuclear energy is harnessed. Now, when it comes to nuclear energy, it's important to note that the protons and neutrons, otherwise called nucleons, in the nucleus of each atom are held together by very powerful nuclear forces. Now, an enormous amount of energy is required in order to tear this nucleon apart by separating the protons and the neutrons. Enormous amount of energy is required. Enrico Fermi, born in 1934, discovered that the nucleus can be split by bombarding it with a slow neutron. A nucleus can be split by bombarding it with a slow neutron, and that is how nuclear energy is created. Now, further on Enrico Fermi, he discovered that the total mass of the components produced is less than the mass of the original materials. So when this nuclear energy is released, new elements, new products are brought into existence, and the component products, the byproducts that are being released or produced, are less in mass than that of the original materials from which they came. The difference in this mass, which is called mass defect, is a measure of the nuclear energy that has been released. And according to Albert Einstein, he said that the nuclear energy released is equal to the mass effect and multiplied by the velocity of light squared, which is c. So energy released equal to mass effect, that is change in mass, which is original materials, mass of original materials minus the mass of the component products, and then you multiply by the speed of light squared, which is 3.0 times 10 raised to the power 8 meters per second. Now let's talk about nuclear fission. Well, nuclear fission simply refers to the splitting up of the nucleus of a heavy element into two approximate equal parts with the release of a huge amount of energy and neutrons. Fission occurs with most of massive nuclei. So when the heavy nucleus is bombarded by a slow neutron, several neutrons are produced as byproducts. These neutrons may cause the splitting of other nuclei, which in turn yield more neutrons, which may further split other nuclei, and so on. Thus, this leads to a chain reaction which is set in motion. So, more neutrons are split. When they are split, they form another nuclei, and the nuclei is also split, yielding more neutrons, and they further split into other nuclei, and so on. And so this forms a chain reaction. A spontaneous reaction is set in motion. Now, when we talk about a chain reaction, we're simply referring to a self-sustaining process, a self-maintaining reaction, a multiplying reaction. So when the size of the nuclei exceeds a certain critical mass, there is a rapid production of neutron accompanied by a release of tremendous amounts of energy in a nuclear explosion. This is the principle of the atomic and nuclear fission bombs. It is also the process that we use today in present-day nuclear power stations. The opposite of nuclear fission is nuclear fusion. Remember, fission is the breaking down of atoms to form nucleus, and then when the neutrons are introduced into them, a slow neutron is introduced, they also break down further and huge amounts of energy is released. Fusion, on the other hand, is the combining or fusing together. When they combine, when two separate light nuclei combine or more, they form a heavier nucleus, and at the same time there is a release of a large amount of energy. So what it simply means is that when it comes to both fission and fusion, this one is the breaking down and this is the combining or fusing together. That is what it means. Either way, both of them, one thing they share in common is that there is a release of a huge amount of energy, and that is what makes this process so powerful. For example, let's say if you want to bring two light nuclei together in a fusion process, say for instance hydrogen, you would need a very high temperature to overcome the Coulomb repulsive forces between the two nuclei. Now let's talk about the advantages of fusion over fission. There are about three of them. The first is that fusion is more easily achieved with light elements. The lightest element in the periodic table is hydrogen, whereas fission, on the other hand, requires more bigger elements, heavier elements to achieve its aim. The second is that raw materials required from fusion are more readily and cheaply available, whereas materials from fission are more expensive. Fusion processes produce less dangerous byproducts, whereas fission processes produces very extremely dangerous byproducts. When you hear nuclear energy, jettison the fact that it is not always all bad. There are also some peaceful uses of nuclear energy. Four of them. The first one is that many nuclear power plants today are being used to generate electricity. We have several fission products also that are obtained in nuclear reactions, and they are used for radiotherapy in the treatment of cancer. We also have radioisotopes from nuclear plants that are used in agriculture as preservatives and as tracers. And then in some spacecraft ships and submarines, they are also powered by nuclear energy, hence their ability and capacity to cover huge distances and for submarines to remain submerged in water for a very long period of time. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.